Hello, welcome. And before we start, I want to clarify that the lecture videos are not going to be a replacement for the notes posted in Canvas. So before you watch these videos, make sure you read the notes carefully, follow the links to understand the information there and be able to practice some of the stuff that I have provided. Now, today we are going to focus on reactions of carboxylic acids and their derivatives. And what you notice here is that the carboxylic acid and the derivatives contain leaving groups which are attached to the acyl. Okay? So the nature of the leaving group is actually going to be able to determine the reactivity of the carboxylic acid derivative. So in other words, how stable and how fast the leaving group can be kicked out is the one that controls the reactivity. So to be brief, acid halides are the most reactive, followed by acid anhydrides, esters, and then amides. Now, nitriles are also grouped under this category because they react in a similar fashion to the carbonyls. So if you have a nucleophile, we can be able to install the nucleophile on the carbon of the nitrile, and we will be able to create a product or an intermediate that looks like this. So what you can see here is we have installed a nucleophile, and then now the nitrogen is able to accommodate the charge, the minus charge, just like the oxygen of the carbonyl. Okay. To understand the reactions of carboxylic acids and the derivatives, we are going to look at the nucleophile that we are utilizing to do the attack. So we're going to use water, we're going to use alcohols, we're going to use amines, we're going to use hydrogen nucleophiles. We are going to use a Grignard reaction, so these are carbon nucleophiles. And then we're going to look at the processes involved. For example, when we use water, that's going to be hydrolysis. If we use alcohol, we're going to call it alcoholysis, and that is due to the fact that we are cleaving off the substituent, which we said is acting as a leaving group and being able to control the reactivity. Okay? So the acid halides being the most reactive and actually able to undergo these processes, we're going to start with that, and then we are going to go into the other functional groups. So when reacted with water, the acid halides undergo hydrolysis to form carboxylic acid. And we can also transform them into esters if we perform a reaction that involves alcoholysis. For aminolysis, we can use ammonia, we can use primary amine or secondary amine, so we can end up forming primary amide, secondary amide, or we can form a tertiary amide. Now, in these cases, we require excess of the ammonia or amine compound because the product that's generated is an acid, and the excess amine helps to neutralize the acidity. With hydrogen nucleophiles, we can perform a reduction to generate a primary alcohol, or we can actually do a reduction using a bulky hydride, and for example, we could use So we could use something like tri-tert-butoxy lithium aluminum hydride, which is bulky enough to avoid a direct reduction all the way to a primary alcohol. So instead it reacts to generate an aldehyde and stops there, so the aldehyde can be separated and purified. With Grignard reaction, we can form tertiary alcohols, and then with Gilman reagent, this is unique to acid halides. They specifically react with Gilman reagent to form a ketone. So now we can classify these 6 kind of categories of reactions, and the transformation of the products formed will, as we have realized, depend on the nature of the nucleophile that has been used. Continuing to acid and hydride, they're able to undergo hydrolysis to form carboxylic acid. They're able to undergo alcoholysis to generate an ester. We can use the excess of amines to form primary amides, secondary amides, tertiary amides. With hydrogen nucleophiles, we can be able to transform it into primary alcohol. And we can also do reduction using Grignard reagent to form tertiary alcohol. So moving on to the esters, and by putting everything together, we're going to realize that now the esters are not going to be able to undergo some of the reactions we already looked at. So they can undergo hydrolysis to form carboxylic acid. They can be able to undergo reduction to generate primary alcohol. That is, if we use lithium aluminum hydride, and of course excess of that. And we can also be able to stop the reaction at the aldehyde if we use a bulky hydride, similar to what we studied under the synthesis of the aldehydes. The other reaction they are likely to undergo is the amination process, but this is very slow, so it's not quite practical. With nitriles, it is possible to transform them into amines if we do reduction using lithium aluminum hydride. We can also be able to do hydrolysis to transform them into carboxylic acid. And the other reaction we could do is you can use a Grignard reagent, that is CH3 MgBr, and we can follow that with say water to form a ketone. Amides can only undergo a few reactions under these processes. Specifically, the primary amide, we can transform it into a nitrile. If we use thionyl chloride, we can also be able to do hydrolysis, which is a very slow process for this reaction. And then the other reaction we could do is to transform amides into amines if we use lithium aluminum hydride. So I actually got a table here that gives a complete summary of the transformations and the kind of functional group that you want to transform. So assuming you want to transform an acid anhydride, for example, into an alcohol, then we just need to find out which transformer it is. So we need to use lithium aluminum hydride. That will be able to give us a primary alcohol. So I would want you to review this, and then later on we are going to look at some of the examples and do some practice on the synthesis and how we can generate some compounds based on these strategies. So until next time, I wish you the best. Have a good one, and thank you for watching.